So again, with stoichiometry, we're just interconverting between mass and moles, moles and moles. And so there are different types of stoichiometry problems. The one presented here is where we have the mass of one reactant and an excess of the other reactant. And so since we have an excess of one reactant, we know that the other reactant that's not in excess is going to be all consumed. And so the amount of product produced by the what we call the reactant that gets used up, or the limiting reactant, is referred to as the theoretical yield. So anytime you see the theoretical yield, that's the amount of product produced by the reactant that gets completely consumed in the reaction. So in this example, we have hydrogen gas plus oxygen gas because it's H2O. So H2O is our only product, and we want to know how much H2O can be produced if we use 4.5 grams of hydrogen gas with excess oxygen. So that excess oxygen means there's more than enough oxygen to be to use for this reaction. So hydrogen is going to get completely consumed. And notice here it gives us 4.5 grams of hydrogen. So what we're going to do is we're going to take the mass of hydrogen, convert it to moles of hydrogen, and then convert it to moles of water, and then mass of water. And you're going to be seeing the same kind of pattern over and over for stoichiometry problems. So we need a few things before we can actually do this. One is we need to look at the balanced chemical equation, and we notice that there's a 2 in front of hydrogen and a 2 in front of water. So what this means is that for every 2 moles of hydrogen, we produce 2 moles of H2O. So we can say 2 moles of H2 equal 2 moles of H2O. So that's our equality between the reactant and the product. Secondly, we're going to need the molar masses. So the molar mass of H2 is 2 grams per mole. If we just say hydrogen's 1 gram each. And for H2O, it's 18 grams per mole. So now we have the molar masses, we have the equality, or the conversion factor, if you want to call that, between H2 and H2O. So now we can set up our train tracks and convert between the two. So again, we're starting with grams of hydrogen. So we have 4.5 grams of H2. Now that we have the grams of hydrogen, we want to convert it to moles, so we divide by the molar mass. So 2 grams of hydrogen for every 1 mole of hydrogen. Here's where we convert between the moles of hydrogen and moles of water. Again, you notice it's 2 to 2 relationship, so 2 moles of hydrogen produce 2 moles of water. You can just rewrite that as 1 to 1. Or you can keep it 2 to 2. It's going to give you the same result. So now we have the moles of water. Then we want to convert it to mass of water. Since we're starting with moles of water, the mole goes on the bottom. The mass goes on top. And again, you notice that everything cancels but the mass of water. So we multiply everything on top, we divide by everything on the bottom. And we get 41 grams. Or if you want to do it to 3 significant figures, 40.5 grams of water. So if all the hydrogen gets consumed, we produce 40.5 grams of water. And this is referred to again as the theoretical yield. So the theoretical yield is the maximum amount of product that can be produced by the reactant that gets completely consumed. Now for limiting reagents or limiting reactant, however you want to say it, we're looking at which reagent gets all used up in the reaction. And again, what you learn about stoichiometry here, we're going to reuse this principle when we talk about aqueous solutions, when we talk about gases, and when we talk about energy. So you're going to see this type of stoichiometry is what they call it throughout the next series of topics that we discuss in Gen Chem 1. So you're going to see it here, you're going to see it when we talk about aqueous solutions, you're going to see it when we talk about gases, and also energy or heat. And there are 5 steps that we typically take when determining the limiting reagent. Of course, you always need a balanced chemical equation. That's very important because if you don't get a balanced chemical equation, your mole ratios are going to be incorrect. And then if your mole ratios are wrong, everything else is going to be wrong. Secondly, if it gives you mass, or if it gives you any type of quantity, it doesn't have to be mass, as we'll see in later chapters, but it gives you, for example, in this one, mass, we have to convert it to moles, because the way we go from reactants to products is through moles, so we got to convert to moles. Then in step 3, we use the mole ratio to convert to moles of the product we want. Then we look at which one produces the smallest amount of product, and this is the reactant that's the limiting reactant. Once you know the limiting reactant and the theoretical yield, you can determine how much of the excess reagent is left over. So one reactant is going to get consumed, the others will be in excess. And these are the steps we're going to be doing every time when we're looking for limiting reagent. Will be steps 1 through 4. When we're looking for excess reagent, steps 1 through 5. So I'll kind of walk you through a flow chart or a diagram of what we'll be doing, and then we'll look at some examples of this. So here we want to know how many grams of solid aluminum sulfide can be prepared by a reaction of 10 grams of aluminum and 15 grams of sulfur. And then secondly, how many grams of excess reactant is left over. So different to the example we just did, here you see we're given information or the mass of each reactant. And we're asked how many grams of the product can be prepared. So first, what we're going to use is we're going to need a balanced chemical equation. From the balanced chemical equation, we're going to take the mass of each reactant. Using the molar mass, we're going to convert those to moles of each reactant. Then the mole ratio from the balanced chemical equation, we're going to get the moles of aluminum sulfide, and then we determine whichever one of these is the smaller one, we're going to convert that to mass of aluminum sulfide. And this is referred to again as the theoretical yield. So we're going to be doing the same process that we did in the previous example, except we're going to be doing a duplicate of it. And there's different ways you can approach limiting reagent problems. If you have a different approach and it works, that's fine. This is the approach I'm going to use. Now, once we determine the theoretical yield, then what we can do is find the excess reagent. So we're going to take the mass of product produced from the limiting reagent, and actually we should say this is going to be the moles, because to use mole ratio it has to be moles. So we take the moles of product from the limiting reagent using the mole ratio. We convert it to the moles of excess reagent, and then we can get the mass of excess reagent used. And then to find how much is left over, we subtract it from the initial amount. So this process is going to be replicated every time we do a limiting reagent problem. And if we're doing an excess reagent, we're going to be replicating the same process as well. So once you understand the process, it's just simply a matter of plugging in numbers and getting the different quantities. Now, if you want to see this worked out, so here's our balanced chemical equation. Remember, sulfur is octaatomic, so it has to have 8 unless it's specified otherwise. And we have our balanced chemical equation. So the first step, we're going to take the mass of aluminum, convert it to moles of aluminum sulfide, and we're going to do the same thing with sulfur. So again, mass to moles, moles to moles. We get the number of moles of product produced by each reactant. Notice here that sulfur is the one that has fewer moles, so that's going to be our limiting reagent. So from that, we can get the theoretical yield of our product. Again, this is called the theoretical yield. But don't think that every time you have this reaction, you're going to have the same limiting reactant, because that can change depending on the mass of reactants you have present. In this example, sulfur is the limiting reactant, but it doesn't mean in every example with this equation, sulfur would be the limiting reactant. So next we want to find the excess reagent. So we take the moles of the product produced by the limiting reagent, and we're going to convert it to moles of the excess reagent. So that's aluminum. So in the first step, we're converting moles of aluminum sulfide to moles of aluminum, and then we convert that to mass of aluminum. So this 8.424 grams is how much aluminum is used. And then we subtract it from the initial, which was 10, and we see that we have 1.58 grams of aluminum left over.
Dr. Mana?
So now we'll look at a example here involving theoretical yield. So we want to know how much chromium can be produced by the reaction of 40 grams of chromium 3 oxide and 10 grams of aluminum, given the chemical equation below. So the first thing we need to do is balance it. And so since aluminum and chromium are both individual elements, it's going to be very easy to balance those. So the oxygen is already balanced, so to balance the aluminum, we just put 2Al. And we have our balance chemical equation. So that's the first step. So now what we need to do is we need to determine the amount of chromium produced by each reactant. So we're going to do a duplicate set of calculations. We're going to do one for chromium 3 oxide, and we're going to do the exact same thing with aluminum. And so we need some molar masses. So the molar mass of chromium, 52.0. Molar mass of aluminum, and the molar mass 152. So now we have the molar masses of the reactants and products that we need. So again, what we're going to do is we're going to start first convert for chromium 3 oxide, convert the mass of chromium 3 oxide into moles of chromium, and do the same thing for aluminum, convert the mass of aluminum into moles of chromium. So what we know with chromium 3 oxide is that 1 mole of Cr2O3 equals 2 moles of Cr. And then for aluminum, we know that 2 moles of aluminum equal 2 moles of chromium. So those are mole to mole ratios. So now we can start plugging and checking. So again, we're going to be doing the exact same thing for both reactants. So we start with the mass of chromium 3 oxide. We convert that to moles. And then we convert it to moles of chromium. We do the exact same thing with aluminum. So we start with the mass of aluminum, convert it to moles, and then convert it to moles of chromium. And since it's 2 to 2, you can just put 1 to 1. So now we can determine the moles of product produced by each. And so we notice here that aluminum produced a fewer moles of chromium. So aluminum is the limiting reactant. And so from this, we can now determine the mass of chromium that will be produced, that could be produced. And we get 19.2 grams of chromium. And again, that's the theoretical yield. So again, I hope it's noticed that we're doing the same set of calculations each time. So we'll look at another example involving a limiting reagent. So here we want to determine the amount of excess reagent left over when 105 grams of hydrogen gas reacts with 115 grams of nitrogen gas. So we have this reaction involving hydrogen and nitrogen to produce ammonia. We want to know how much of the excess reagent is left over. So in order to determine the excess reagent, we have to first determine which one is the limiting reagent. So again, what we need to start off with is a balanced chemical equation, and notice that this equation is not balanced, and you have hydrogen and nitrogen that are both not balanced in this equation. But I would recommend starting with hydrogen because hydrogen is an even odd combination. So you have 2 hydrogen on one side, 3 hydrogen on the other, whereas nitrogen it's a 2 to 1. So as long as nitrogen is even on the product side, we can balance it very easily on the reactant side. And so the common multiple between 2 and 3 is 6. So this becomes 3H2. We'll come back to N2 and 2NH3. So you see here, this by putting the 2 in front of ammonia, we have now 6 hydrogen on both sides, 2 nitrogen, so it's a balanced chemical equation. So again, we're going to do a duplicate set of calculations. We're going to do one for hydrogen gas, and we're going to do one for nitrogen gas. Now, by looking at the balanced chemical equation, we know that 3 moles of H2 equals 2 moles of ammonia, and for N2, 1 mole of N2 equals 2 moles NH3. We need some molar masses. Molar mass of H2, molar mass of N2, and molar mass of NH3. Set up our train tracks. So again, we're doing all this to determine the limiting reagent. So we'll start with H2. We have 105 grams. I'm going to convert that to moles. And then we can convert that to moles of ammonia. We're going to do the exact same thing, but with nitrogen. So we start with the mass of nitrogen, convert it to moles. And then convert it to moles of ammonia. Notice we're doing the exact thing, same thing for both. We'll just put in different numbers for each. Multiply what's on top, divide by what's on the bottom. This is 35 moles. Double check my work. So from this, we know that nitrogen is the limiting reagent. So we can determine the theoretical yield. Or actually, we don't need to because we don't need it in grams. We just need to determine the excess reagent. So now we know that this is the theoretical yield. And again, we don't need to convert it to grams because we're interested in the excess reagent. We're not interested in the mass of theoretical yield. So I'm just going to stop here. And now for the excess reagent, we need to convert the moles of ammonia into moles of excess reagent to see how much of the excess reagent we used. And that we need to convert to mass. So again, we have 8.21 moles of ammonia. We're going to convert this to moles of hydrogen. And then we're going to convert it to mass of hydrogen. This will tell us how much hydrogen was used in the experiment. And we get 24.6 grams. And again, this is how much is used. By the way, if the amount used is more than the amount you started with, there's something wrong with your calculation. So the use should always be less than the amount you start with because it's an excess reagent. So we found the mass of hydrogen that was used. We initially started with 105, so the excess hydrogen would be 105 minus 24.6. And that would be 75.4 grams. And again, this is the excess. So that's how much hydrogen is left over. So if you wanted to do this reaction again, you could keep the same amount of hydrogen and add another 115 grams of nitrogen gas, and it would do the reaction again. So in summary, we're looking for the excess reagent. We first have to determine which reactant is the limiting reagent, and then find the theoretical yield of product produced by the limiting reagent. Once we understand that, we can convert the moles of product or the theoretical yield into the mass of excess reagent used. Once we know how much it was used, we can subtract it from the initial amount and we get how much is left over. So the only component of stoichiometry that's missing is percent yield, which will be covered in a later lecture. So that's all for this lecture. I'll